Hello, everybody. Dr. Maxwell here from the Department of Geospatial Science at Radford University. And I'm going to be sharing another tutorial here on how to use the treeclim package in R to do your climate response analysis for dendrochronology. So let's start out again with the screen share. Here we have our setup for Rstudio. And I have some code already programmed in to analyze our chronology. If you need to build a chronology, I do have a previous video on how to create a chronology in R. But briefly, I'll go to the top of my code here, and we will need to read in an RWL file, name it something, make sure that it's accurately dated. Then you can go down to the RStan stuff where we do detrending and standardization. And you would run a function to detrend all of those series, and then you would create either a residual chronology or you would create a standardized chronology. And I talk about that in the previous video as well. I already have these programmed in, and for this analysis with the climate data, I will be using the residual chronology that has autocorrelation removed. Now, if we go down to the treeclim code, we want to make sure first off that we have our libraries loaded in so we can use the functions in the treeclim package. Then we want to make sure that we are setting our working directory so that any graphs that we save or tables will be saved there. And now we need to read in some climate data. Let me show you what the climate data looks like. I downloaded and formatted this from the Prism climate group. And this is monthly climate data with a year and then the 12 columns for the months of the data. What we're looking at here is precipitation for Salude Conservancy in Southwestern Virginia, part of the Radford University property. And so we want this monthly data to analyze how trees respond to specific months with their annual ring width growth. You can format this data using Prism code that I have up on my Tree Ringer GitHub page if you so like. But we do need to read that data set in. And so the first thing we're going to do is read in that CSV file and call it clim for climate data. If we wanted to plot that, you can use the ggplot package. Highly recommend that one. There's a great cheat sheet for it up in the help menu up here. And you can get the ggplot2 cheat sheet. Really handy for quickly making plots of your data. And then you can also really customize a lot. And so here's just a bit of code to do that. And if we run that and hit the plot, I just made a quick plot so you could see the change in June precipitation over time. You can plot multiple months if you would like, or you may just want to examine a specific month. And I was just changing the variable that I could plot there. And so X6 is the 6th month of the year, and that's June precipitation. So just different ways to visualize that. And just as a reminder, if you'd like to save any of these, just go to the export menu and save image as. So now that we have our climate data read in, we really have one key function in the treeclim package, and it's called DCC. And so let me walk you through this. So I'm going to be calling the function DCC, and I am going to be naming the output response here, our RESP. Within the function DCC, we have several arguments that we have to make sure that we address. So let me just pull this open a little bit more. And so the first one is, what chronology are we pulling in? Well, we've already used the DPLR package to create grow.chron. And so we're going to call up that data set or that data frame. For the climate data, we just read in the climate data. And so that is in a 12-month format. And that's what treeclim is meant to analyze. Then we need to select which months that we want to analyze and correlate with our tree ring data. Now, I often want to analyze the data from the previous growing season because I want to see if that climate has an effect on the current year's growth. We often have that lag effect because trees are going to be storing carbohydrates, and that may influence the growth in the next year. So if you have a good year last year, maybe you have a good year this too, or it ameliorates some challenges of a drought in the current growing season. So because we're looking at precipitation, this lag effect may occur. And so here I have -5. And so that's May of the previous growing season to 10, which is October of the current growing season. So this is a large window that covers the entire growing seasons for the current year and the previous year. For our method of analysis, we can use either the word correlation in here, or we could use response. And so do we want to calculate a response function, which is a linear relationship, just like a correlation, or correlation analysis using something like this Pearson correlation coefficient. So we'll use correlation for this. Then we use a method that's either dynamic in the sense that it could be a moving correlation, and we'll do that one here in a second, but we're going to start out and do a static. And the static correlation here will do a comparison of the overlap in the tree ring series between the tree ring data and the climate data. And so we have climate data going back to 1895, and we have tree ring data going back that far as well. And so we can compare that entire period of overlap up to present. And that will give us one value or one correlation value for each month of climate data. We'll come back to this argument window size in a little bit and the other variables. What this program does is it doesn't calculate a simple correlation coefficient. It actually, well, it does, but then it bootstraps it 1,000 times. And this bootstrapping is helpful because it can help us generate confidence intervals around our estimates for the correlation values. And you can just use the standard method here for that bootstrapping. And then, of course, we can set our confidence intervals, and I just leave this to 0.05. Now, we can highlight this and run it and interpret our results. So I am just going to select there, put my cursor at the response, and hit run. I now am just going to say, okay, we'll read in those coefficients that it just calculated, and we can display those. And if we look down in our console, we can see the correlation coefficients from the previous May all the way up to the current October, and it will tell us if these are significant or not. So true and false, saying true being significant, with our confidence intervals. Now, we could use that and save that as a table. That could be pretty helpful. So you could do a write.csv function, but we can also plot that. And so to plot that, we run just a quick plot function. And if we zoom in on that, we can now see our results. And the way we read this is here we have correlation coefficients on the Y, and on the X we have the months, with the previous growing season being lowercase and the current growing season being uppercase variables here. Now, what we're seeing is that we have significant responses in June and September of the previous growing season, meaning that increases in precip lead to increases in tree ring width in the following year. And that makes sense if we have a wet growing season where the trees can do a lot of work and a lot of photosynthesis and store some carbohydrates, perhaps. That can be beneficial in the following year. In the current growing season, we have April, May, and June showing positive and significant correlations with tree growth. And that makes sense too, where you have in this region of Virginia, the growing season starting in April. And these are white oak trees that put on those big, large vessels immediately in the spring. And so we would assume or hypothesize that we would have a positive and significant relationship with growing season precipitation. And so you want to make sure that when you have these correlations that you can accurately interpret them, because sometimes we do get spurious correlations that can be a little bit challenging to interpret, especially when you see positive or negative relationships that are significant in the wintertime. You need to make sure that you can connect that to the biological growth of the tree. So that is the static analysis using the complete period of overlap between tree growth and climate. Now we can go back to our function here and we can alter this dynamic to moving. Moving analysis will take not just the complete period of overlap, but it will look at a 35-year window or a window of our length. But you do want to keep it around 35 years because we want to have a large enough sample size, or N, to calculate a significant correlation. When you drop it too low, you have to have a very high correlation for it to be significant at the 0.05 level. And we also need to control for degrees of freedom. We can set the offset to 1 here. And so what it will do is increment that 35-year window 1 year at a time. So it'll start out in, say, 1895, go up to 1930, and then it'll increment to 1896, 1897, and it'll just keep moving that window 35 years through time. Start last would mean let's start at the inside of the tree or the earliest climate year that we have, and then it will move it forward in time. Now, we can change some of these other things if we'd like, but I recommend that you just leave the confidence intervals and the bootstraps to a standard setting once you figure out the type of analysis that you want to do. Now, this analysis will take slightly longer for the computer to calculate because it is calculating a 35-year window. It's bootstrapping that 1,000 times, and then it is doing that for each month as well. And it's just incrementing that 35-year window through time. So it's calculating many correlation values. Okay, it's already done. So we could look at those coefficients. That's going to be a rather large table of coefficients. That would be difficult to interpret. And so it would be best to just plot that data. And so if we run the plot function, we can see our plot pop up over here. And this is a little bit more challenging to interpret if you haven't seen these graphs before. So let me enlarge this a little bit better. What we're seeing here is we have the current October up here and the previous May down here. And so each one of these rows represents the correlation values over time between the monthly climate variable and the annual ring width. And then on the axis down here, we see the X axis is showing us 1896 to 1930. Well, that is the first 35-year window, and then it increments it to 1897 to 1931. So each of these rectangles represents a correlation with the 35-year window moving through time. The asterisks show that that correlation is not only positive or negative in that region, but it is significant. And so blue is showing a positive relationship while reds are showing a negative relationship. And so we do see that our current growing season shows significant relationships, but there is some variability in those relationships over time. This can be caused by various things. It could be changes in the stand that we're looking at, the forest stand that we're looking at. Maybe there was some disturbance in the stand where the trees are responding more to that than to climate. That's certainly a possibility. But perhaps there was also a change in the climate that was driving a change in the climate growth response. And so maybe there was a shift in precipitation from one month to another, or an increase or decrease in precipitation over time in a specific month. Ideally, we would like to see these relationships strong and consistent over the entire duration of our analysis. And I would say the June relationship is pretty stable over time, even though it weakens perhaps in the early 1900s. Now, the previous June relationship, this is a more recent phenomenon, and we see an increasingly positive and significant relationship here. The September relationship is still relatively weak in the previous growing season. Again, we want to make sure that we can interpret these relationships. And if they do change over time, the next question you should ask yourself is why? And that's why it is good to plot some of your data using the ggplot or other types of plot functions to examine is it a change in the climate variable that may be driving this, or is it a change in how trees are responding to the environment at your site, maybe due to ecological factors. Perhaps you have fire in your ecosystem or insect outbreaks and so forth, and you want to make sure that any of those changes are investigated. Now, we can look at some of this a little bit differently. If we wanted to pull out certain months, we could change our variables in here and then just plot those and trace them over time. We can write our data to a CSV file, and we could even just save our plot as a JPEG if we wanted to with this function. Otherwise, what I often do for quick analysis, I'll just save the image over here. And that is the basic premise of running treeclim. There is one more function that you can, argument that you can change. Instead of moving, we can use evolving. And the evolving dynamic here will do a slightly bit of a different thing here. I'm going to run this and then tell you what's happening in the background. This is similar to the moving response, but instead of a 35-year window that moves through time, incrementing 1 year at a time, the evolving will start out with a 35-year window from 1896 to 1930, and then it'll grow it to 36 years, 37 years, 38 years, and grow it all the way until it gets to the end of the tree ring chronology, or where our climate data is. And what that does is it allows us to see that as we add in new observations, does the relationship change over time as well? And so you can anchor it towards the pith or the early climate data, or you can anchor it at the bark and grow it backwards in time. These evolving functions are another way to get at how climate growth responses change over time. And the idea here is that we want to make sure that what we're seeing is not a spurious result, that it is consistent over time. And so when we do the evolving analysis, what we do see is that this relationship for June is pretty stable as we grow that window larger in size and use more recent data as we grow the window. And June is pretty consistent. We do see increasing consistency in the previous June and previous September. We could rerun this analysis to see how it would change if we do start last here equals false. And what this will do is start it at the bark and grow that window in size backwards in time. If we run that and then plot it, we'll see our plot come up here. And you want to explore how your trees are responding to climate for various reasons. One, we might be interested to see if that tree growth climate response has changed over time. And if it has, is this something related to how trees are recording the environment, how the climate might be changing? And if so, this may give us some indication of how, say, forest managers might want to respond with treatments and so forth for the forest ecosystem. Additionally, for me, as a paleoclimatologist, I want to make sure that the relationship between the variable that I'm going to reconstruct, like June precipitation, if that has a consistent relationship with our tree ring width over time. If this relationship is inconsistent, this makes it more difficult to adhere to some of the principles of dendrochronology. And we want to make sure that we are reconstructing something that has a consistent relationship, not only now, but back in time. And this is pretty crucial to paleoclimatology. So that is the fundamentals of running the treeclim analysis. There are other packages for climate response functions, and they can use monthly data, daily data, or you can compile months into seasons and run it. But the treeclim package is a good first step to analyze how your data, how your trees are responding to monthly climate variables. So try it out with your own data sets. Again, if you start out with the creating a chronology video, you'll create your chronology and then you can read it in down here with treeclim. All right, good luck on your work, and I will see you on the other side.